Hello everyone, welcome to Algoride. In this video, we are going to learn about analysis of algorithms. In my previous video, we have discussed about what is an algorithm and different kinds of algorithms and their practical applications. In this video, we will go into details of how we can analyze an algorithm. The first one is amortization. Amortization is a method for analyzing an algorithm's complexity by measuring the amount of time taken as well as the amount of space or memory the algorithm uses while it is in execution. The first one is constant time, which is known as O of 1, where O is a term used for measuring the time complexity, which is also called as a big O notation. The second one is logarithmic, which is O of log n, where n is the size of input that is given for a given algorithm at a given point of time. The third one is called linear, which is O of n. The next one is quasi-linear, O of n log n. Then we'll talk about polynomial, which is O of n to the power of x. If x equals 2, it becomes O of n squared, which is a quadratic, and if x equals 3, it becomes cubic, which is O of n cube. Then we are going to discuss about exponential algorithms, that is O of 2 to the power of n time, and then factorial time complexity, which is O of n factorial. If you look into this picture, we can draw a graph or plot a graph between two variables. One is the runtime complexity in terms of big O of n. The other is the input size, which is n itself. In this case, we see that the constant time algorithms are the best performers and the worst performers are the factorial and the exponential algorithms like O of 2 power n or O of n factorial, because the time taken by this algorithm at a given size of input n is n factorial, or the time taken by an exponential algorithm for a given size of input n is 2 to the power of n, which is way bigger than the constant time algorithms. What is asymptotic behavior? Asymptotic analysis is the evaluation of the performance of an algorithm in terms of just the input size, where n is large. In algorithmic analysis, the important idea is to remove the less significant part in terms of measuring the time complexity while the algorithm is executed. For example, if you see this equation, T of n equals 10n squared plus 2n plus 5. Asymptotically, only the higher order term n squared is of significance, because if you add or if you substitute any value for n, let's say from n equals to 1 to n equals to like 100,000 or whatever, the most significant part of this equation is 10 into n squared, which is 10n squared. And the least significant part is either this constant value 5 or 2n. So here the quadratic term n squared is taking the higher order preference than the linear operation. So in any algorithm, if it performs at n squared time, which means that algorithm is taking a lot of time in computation in that particular case. So the time complexity is always measured by taking the higher order term as a significant term, and in this case, which is O of n squared. Degrees of complexity. An algorithm shows different behaviors when exposed to different types of inputs. There are 3 degrees of complexity that are measured: best case, worst case, and average case. Best case is when the input size is small. Worst case is when the input size is large, and average case is with an average size of the input given for an algorithm. Usually, when you design an algorithm, you always think about scalability in terms of the size of input that the algorithm takes. So it's a good practice to design an algorithm where worst case scenario is being handled properly, which means that in terms of a huge input that is given to the algorithm should perform extremely well in the worst case. So if you look at the picture, the y-axis represents the number of operations and x-axis represents the number of elements, and O represents the upper bound, omega represents the lower bound, and theta represents the average case. So the average time taken for an algorithm is always between the upper bound and the lower bound. So you have to accommodate your algorithm in such a way that it behaves pretty well in case of a huge input or a worst case scenario. Space complexity. Space complexity is measured by the amount of space or memory the algorithm takes in terms of a given size of input n, when n is very large. So it is always wise to choose an algorithm which can be optimized in both time and space. The reason is there is always a trade-off between the algorithm's performance in terms of time versus the space used, because some algorithms which take more space perform well than the algorithms which take less amount of memory. So memory is always expensive, because in terms of adding extra memory to your computer system is like adding extra hardware. So you have to design your algorithm in such a way that you accommodate both time and space, that is the runtime, the time taken for the execution of the algorithm, with a limited amount of memory or the available amount of memory, so that you have a best case performance in terms of both space and time. Complexity analysis. In terms of complexity analysis, we are going to learn about constant time algorithms. An algorithm is said to have a constant time when it is not dependent on the input data. So whatever the size the algorithm input is, the runtime is always the same. The time taken to execute this if and else condition is always the same, and it is not dependent on the size of the input, because you are only running through one statement, which is if A is greater than B, you would return true, otherwise you would return false. Logarithmic time complexity, which is O of log n. An algorithm is said to have a logarithmic time complexity when it reduces the size of the input data at each step. For example, if you take binary search. Binary search is like looking up a phone number in the dictionary. So if you have a phone directory or a phone dictionary and you would like to look for a phone number, what you would do is you go into the middle of the book, and if the name you're looking for comes before the names on this page, you look in the first half, otherwise you look in the second half, which means you are dividing the search into two halves. If you find the phone number that you're looking for in the first half, you don't need to look for in the second half. That way, you are reducing the number of searches by 50%. So in this binary search, you continuously perform this search by dividing each half into further halves until you find the particular phone number you are looking for. If you analyze the time complexity here, the equation says T of n equals O of n by 2 plus n by 4 plus n by 8 until you find the particular phone number, which is of constant time. So in this case, you're reducing the size of input by 50%, which is n by 2, and then it goes to n by 4, then it goes to n by 8, and so on. If you compute this equation, which is nothing but an expression of logarithm of n, it's called log n. So the time complexity for a binary search algorithm is O of log n. The binary search is used in various applications like searching for an element in an array, where array is a contiguous memory allocation of a type of inputs. Linear time complexity. An algorithm is said to have a linear time complexity when the running time increases at most linearly with the size of the input data, which means in this case we are trying to find an element 20 in an array of integers. So the algorithm looks at every index of the array from 0 to 6 to find 20, which means it looks the value at 0 and compares with 20. If not found, it moves on. So in the worst case scenario, if 20 is the last element in the array, let's say at position 8, the algorithm has to examine all the positions from 0 to 8, which means the algorithm is growing linearly across the size of the input n. So the time complexity is determined as T of n equals to O of n, where n is the size of the input. Quasi-linear or O of n log n. An algorithm is said to have a quasi-linear time complexity when each operation in the input data have a logarithmic time complexity. Earlier in the previous slide, we have seen O of log n algorithm, which is binary search. In a binary search, we are dividing the array into two halves and then searching each half to find the valid element. Similarly, the quasi-linear algorithms follow the similar pattern, divide and conquer. So in this example, we want to sort the array of integers. So to sort an array of integers in an increasing order, we are dividing the array into two halves and then further dividing the array into two halves until the size of the subarrays is 1. And then we are sorting the subarrays of size 1 and merging them together into a finally sorted array in an increasing order. So if you look at the way of sorting things here, the array is divided into two halves, which means each half is processed parallelly and it takes O of log n time to perform this operation. So the total time taken in this case would be O of log n plus O of log n until n, where n is the size of the input, which is the number of elements in this array. So each operation on each element is taken log n. So it becomes O of n log n. Quadratic time complexity, or O of n square. An algorithm is said to have a quadratic time complexity when it needs to perform a linear time operation for each value in the input data. For example, in this array, we want to sort the integers in the increasing order of their value. So we are performing a swap operation between every two elements in the array. In the worst case, if the array is sorted in a descending order, which means the integers are arranged like 6, 5, 4, 3, 2, 1, and we want to sort them in an increasing order, we would need to perform a swap operation for each value of the input to get it into the right place. So in the worst case, we would perform n number of swaps for each element. So which means the time complexity in this case would be O of n plus O of n plus O of n, like that for n times, which is O of n square. So these kind of algorithms are also known as polynomial runtime algorithms, and the time complexity is measured as O of n to the power of x for any value of x. Exponential time complexity, or O of 2 power n. An algorithm is said to have an exponential time complexity when the growth doubles with each addition to the input dataset. For example, we have a Fibonacci algorithm where we are computing nth Fibonacci number. So the Fibonacci algorithm says if n is less than or equals to 1, you return n. Otherwise, you recursively compute the nth Fibonacci number using Fibonacci of n minus 1 plus Fibonacci of n minus 2. What is recursion? Recursion is calling the method within itself with different kinds of inputs. We will talk about recursion in our later videos, but we will try to understand the logic behind the execution of this Fibonacci series and why it is an exponential algorithm here. If you look at this tree is called as a recursive tree or a recursion tree, which is based on the kind of input that is given to the algorithm. So if you try to understand from a bottom-up approach, you will clearly know how the recursion works here. For example, if I want to compute a Fibonacci of n, where n equals to 1, which means the nth Fibonacci number here, the value is returned as n. If n is less than or equals to 1, we are returning n, which means if n is 0, the Fibonacci of 0 is 0 and the Fibonacci of 1 is 1. But if the Fibonacci of 2 is Fibonacci of 1 plus Fibonacci of 0. So while computing the Fibonacci of 2, we need to compute both Fibonacci of 1 as well as 0. So when the input is equals to 2, we are actually doubling, which means we are computing 2 Fibonaccis. And then when n equals to 3, we are computing 4 Fibonaccis here. Like Fibonacci of 3 equals Fibonacci of 2 plus Fibonacci of 1. And again, Fibonacci of 2 is computed as Fibonacci of 1 and Fibonacci of 0. Similarly, for 4, we are computing 8 Fibonaccis. Similarly, for 5, it will be 10, and for 6, it will grow as 12, which is doubling. So as the size of the input grows, the number of operations are doubling, which means in the equation, T of n equals O of 1 plus O of 2n plus O of 4n plus O of 8n plus O of something like that. And it becomes O of 2 to the power of n if you compute the equation. So when it comes to the recursive tree, if you clearly observe, we are performing duplicate operations in terms of computing the Fibonacci numbers. Like for example, while computing Fibonacci of 3, we are computing Fibonacci of 1 twice under the subtree of 2 as well as under the subtree of 3 as well. Similarly, if you go to Fibonacci of 4, we are computing the Fibonacci of 2 twice under the subtree of 3 as well as under the tree of 4. So the reason for having an exponential time complexity here is due to the number of times we are duplicating these operations, which eventually grows with the size of the input, right? So we can also reduce this number of duplications or recursive operations through a different programming technique called dynamic programming using memoization that we can discuss later in our future videos. But to just give you a context of why we are seeing an exponential time here is due to the formation of this recursive tree and doubling the size of the operations based on the input that is being provided for this algorithm. Factorial time complexity, or O of n factorial. An algorithm is said to have a factorial time complexity when it grows in a factorial way based on the size of the input. In this case, This person wants to find a shortest path beginning from his city, exploring all the cities given in his path. For example, if there are n number of cities, there would be n factorial ways for this person to find the shortest path by exploring the path and selecting each and every city. So if the number of cities grows, the time taken for finding the shortest path grows as n factorial. So this is a brute force approach in figuring out the shortest path and very expensive. There are other techniques or algorithms like Distra's shortest path algorithm to find the shortest path between 2 points, which are pretty good algorithms than a brute force or a naive approach followed in this case, which is n factorial. So if any algorithm which is taking an factorial amount of time is considered as an expensive algorithm in design. In this video, we discussed about the analysis of algorithms with various topics like amortization and asymptotic behavior, the significance of higher order term in terms of measuring the time complexity. We discussed about the runtime complexity, we discussed about space complexity, the trade-off between space and time complexities. We learned about degrees of complexity such as best case performance, average case performance, and worst case performance of algorithms. We learned about complexity analysis using constant time algorithms, logarithmic algorithms, quadratic or polynomial runtime algorithms, exponential algorithms, and factorial algorithms. In my future videos, I will do coding sessions for different kinds of algorithms like searching, sorting, graph, and then move on to data structures part. If you like this tutorial or video, please share, subscribe, and comment. Thank you.